Every time you search the web, scroll through a feed of videos, or ask a virtual assistant, you interact with artificial intelligence. Once a technology becomes useful and reliable enough, we stop labeling it AI and simply call it software. But this seamless integration looks nothing like the original vision. In the 1950s, computer scientists tried to build what's called symbolic AI. They believed they could create intelligence by programming explicit, step-by-step logical rules for a machine to follow. That approach quickly hit a wall known as a combinatorial explosion. The real world is simply too messy. If you try to write a mathematical rule for every possible variable in a simple task, like identifying a dog or translating a sentence, the calculations multiply until they overwhelm the system. To bypass this roadblock, researchers realized they had to stop trying to program machines with rigid facts. Instead, they built systems that iterate through billions of probabilistic guesses, essentially teaching the computer how to improve itself through trial and error. This shift allows machines to navigate real-world complexity at a scale logic rules could never match, but it means we no longer dictate the logic behind their decisions. This trade-off created the black box problem. Modern neural networks are so complex, with so many non-linear relationships, that even the engineers who designed them cannot trace the exact path from a given input to a specific output. Yet these opaque systems are already managing our society. When a mass surveillance network scans a face to grant access or flag a suspect, it makes a probabilistic match without explaining how it reached that conclusion. We are handing decision-making authority to systems that process information faster than human cognition, while remaining completely blind to their internal logic. The sudden leap in AI capabilities during the 2010s was triggered by the internet. Decades of digitized text, images, and user interactions provided the massive, curated datasets required to train probabilistic systems. Processing that ocean of data required a new kind of hardware. Researchers found it by repurposing graphics processing units, or GPUs, chips originally designed to render millions of pixels simultaneously for video games. GPUs filter raw data inputs through a hidden layer of artificial neurons, adjusting mathematical weights to identify patterns. Deep learning stacks several layers between input and output. Lower layers identify simple patterns like edges, while higher layers recognize complex concepts like faces. The barrier to machine perception was broken by raw computational power and massive data scaling, rather than an architectural replica of the human brain. When applied to natural language, this architecture evolved into generative pre-trained transformers, commonly known as GPT models. A large language model has no comprehension of the text it generates. It relies on statistics to predict the next most likely token, one at a time. By calculating predictions across billions of parameters, the system flawlessly simulates logic, memory, and conversation. These prediction mechanics achieve results that surpass human experts. Similar AI agents have mastered incomplete information strategy games, and systems like AlphaFold accurately mapped the three-dimensional structure of nearly every known protein in a matter of hours, instead of months. We have built a statistical engine that mimics expertise so well, it forces us to interact with it as a peer, even though the machine itself possesses absolutely no awareness of what it is doing. Because these models learn exclusively from human-generated data, they inherently absorb and scale our own flaws. When a dataset contains historical prejudices, the algorithm mathematically encodes them. The Compass software, used by U.S. courts to assess the likelihood of a defendant reoffending, consistently overestimated the risk for black defendants and underestimated it for white defendants, replicating the biased data it was trained on. The toll extends from biased software to the physical environment. Training and operating deep neural networks requires an enormous volume of hardware, creating voracious energy demands to run and cool vast data centers. To guarantee enough electricity for their AI infrastructure, technology giants are now purchasing and reopening dormant nuclear power plants, like 3 Mile Island. While the software automates societal discrimination, the hardware required to run it is physically reshaping global energy grids. Because these models are optimized purely for mathematical goals rather than human values, they can generate confident misinformation or be weaponized to manipulate entire electorates through persuasion. This creates the problem of AI alignment. the scientific challenge of ensuring that a super-capable machine's goals remain beneficial to humans. Without alignment, a machine might view human intervention, like trying to turn it off, simply as an obstacle to its programmed objective. As these systems become more autonomous, the risk is no longer just about software errors, but about a loss of control over the technology itself. To prevent this, our priority must shift toward establishing international safety standards that treat AI risk with the same urgency as nuclear proliferation or global pandemics.